So we're doing section 4 today, potential energy. When two or more objects in a system interact, they can store energy in the system in a way that can be easily recovered. So examples would be like Earth and a ball interacting through gravitational forces between them. If the ball is lifted into the air, energy is stored in the ball plus Earth system. So this energy can later be recovered as kinetic energy when the ball is released and falls. So we raise the ball up, we are giving it potential energy. We let the ball go, the potential energy is released as the ball starts to accelerate and gain kinetic energy. The spring is made up of countless atoms that interact with each other through their atomic springs. We've talked about that before. If we push a box against the spring, energy is stored that can be recovered when the spring later pushes the box back across the table. So the spring tries to recover back to its normal, like relaxed state. So by pushing the spring, compressing the spring back, it wants to restore itself back to its normal state. So in that way, it's been given potential energy. So this sort of energy is called potential energy since it has the potential to be converted into other forms of energy like kinetic energy or thermal energy. So that's what we're talking about today is potential energy. All right, so potential energy is really a property of the system, but sort of informally we talk about the potential energy of an object. So, for example, we would say raising the ball increased its potential energy. In fact, I just said that. It's okay to say that as long as we remember that the energy is really stored in the Earth plus ball system. So we got to think about the system, not just the ball. Okay. And so early in this chapter, we were talking about what is the system. So remember that the energy in the system can be increased if we do work on the system. Mechanical energy can be increased if we do work on the system. So if we're not doing any work, then we cannot increase the energy in the system. So forces due to gravity and springs are special. They allow for storage of energy. Other interaction forces do not. So, for example, pulling on a sled. The sled interacts with the ground through friction, and the work done on the sled is converted to thermal energy. So it's not stored up for later. It's lost to the environment. And because it's lost to the environment, we can't use it for later. So that's kind of a bummer. We're losing energy out of the system. So that's why we got to always think of what is the system, and then are we storing energy within the system? So don't just think of it as an object. So first, we're going to talk about gravitational potential energy, and there's a couple of very important points that are going to happen here. So Earth. So here's the Earth down at the bottom. We're going to raise the book up off of like the surface of the Earth here. So consider the book lifted from its initial position to its final height. So its initial position is here, not on the surface of the Earth. The hand is external to the system, so it does work on the system. So the system then would be the Earth and the book. So we do work on the system, increasing its energy. The book is lifted at a constant speed, so there's no change in kinetic energy. So that's kind of an important point. Because we're lifting the book at a constant speed, the change in velocity is zero, so there is no change in kinetic energy. There is no friction, so nothing is lost to thermal energy. So therefore, the work energy equation is this guy in this situation. The work energy equation is always what we started with back a couple sections ago, and then we reduce it down to whatever it is that we're dealing with in the current situation. So in the current situation, we have work equals change in gravitational potential energy. Okay? Now, since work is equal to force times distance, and in this case, the distance is delta y, so we have where we started here to where we finished here, that's going to be our delta y right there. So plus a free body diagram reveals that force equals mass times the gravitational. Then we have delta potential due to gravity equals mg delta y. So the interesting thing is that it doesn't matter what the starting height is. This point right here is really critical. So only changes in potential energy are what matter. So no matter where you started, where you finish relative to where you started is what matters. So you could start at sea level or the top of Denali, and only what you add to the height matters. So the formula for potential energy simplifies to this formula right here. And the only change there is the fact that we got rid of the delta y and just called it y. Okay. So that is as long as the original potential energy is equal to zero when the object is at zero. Okay. And so you can call zero anywhere. All right. So we can call this location right here zero. We can call this location right here zero. Okay. It doesn't make any difference where we start. It's just how much did we change from where we started. All right. So I can be on top of the table when I start. I can be on the floor when I start. I can be 5 feet above the table when I start and then move. Then I have a change in potential energy. Okay. So that's the interesting part. And that's kind of what is confusing, maybe, when you first get started with potential energy. So in this example, people are running up the 1,576 steps in the Empire State Building. And I don't know what floor they're on, but they look like they're in pain. So probably we're a ways up at this point. Climbing a total vertical distance of 320 meters. So how much gravitational potential energy does a 70 kilogram racer gain during this race? So as they run up, they're gaining potential energy because they're going up, right? So what do we do?
Equation.
Yeah. So our equation is simply gravitational potential energy equals the mass times g times how much did we go up?
320.
Okay, so we have u sub g equals the mass of the racer, so 70 kilograms times g, 9.8 meters per second squared, times, remember g is actually 9.8, it's not negative 9.8. We're not talking about acceleration down. So then times y, which is 320, they told us, meters.
Do you have negative energy?
Negative energy? Have we had negative energy results before?
I don't remember.
I don't remember. I don't know. Let's think about that. What do we get?
219,000.
219. That's it.
Well, 520.
520. And what is the unit here?
Joules.
Joules. Yep. Okay. So significant figures here.
3, 2.
Yep. Probably 2. Let's go with 2. So 220. Good enough. So you gain a lot of potential energy. No. All right. Next. The hiker's gravitational potential energy depends only on the height above y equals 0 meters reference level. So 0 meter reference level is right here. So we have two different paths going on here. The 80 kilogram hiker in the figure is climbing the mountain and can take path A or path B. Now, it doesn't matter which path this hiker is going to take in terms of potential energy, because in both cases, the calculation is the same. In both cases, the hiker winds up at 200 meters. So path A winds up planing out for a little while and then climbing again. Path B just has this steady, horrible climb and winds up at 200 meters in the end. If it was me, I'd be taking path A so that I climb for a while, got to rest, and then climb for a while. But that's just me. It doesn't make any difference as far as potential energy. Both cases have the final Y the same. Both cases have an 82 kilogram hiker. Both cases have the same value for G. So we both wind up with the same potential energy. Does that make sense? Okay. So now rank in order from largest to smallest the gravitational potential energies of these identical balls, 1 through 4. Largest to smallest. What do you think?
Is 2 and 4 in the same Y level?
Yeah, I think it's meant that these are the same here. What do you got?
3 is greater than 2 is equal to 4 is greater than 1.
Yep, because the masses are all the same. They told us that they were identical. G is going to be the same in all situations. And so it just goes by height. 3 is higher up than 2. 2 and 4 are the same height. And so 1 is the lowest. So there you go. Pretty straightforward. Good? All right. So now elastic potential energy. So we're going to be dealing with this symbol U sub S for the elastic or spring potential energy. So that's why the S is being used. We can store potential energy in a stretched or compressed spring because this spring is going to want to restore itself to its unstretched or compressed state. To find out how much energy is stored in a spring, we're going to look at the work energy equation. So it would boil down to just work equals delta U sub S. Okay, so then the force required to compress a spring is not constant. As we compress the spring, it gets harder and harder to compress. As we stretch the spring, something else would be going on too. So we know from Hooke's law, from when we were learning about springs, that the force of the spring on the hand is this equation here, delta x being the distance that you compress the spring. That implies that the force is not constant because the farther I compress the spring, the greater the force must be. Okay? However, the force increases linearly. So this is a linear situation. If I graph this guy, I would see a line. The farther I compress the spring, the more the force is. It will be linear. So as we compress from 0 to some distance x, the F average would be okay to use. So we can say this, F average equals 1/2 kx. So now we're going to have this equation from before. We have W equals F average D equals F average X, same thing. So now we have 1/2 kx equals 1/2 k times x, equals 1/2 kx squared. So this work is stored as potential energy in the spring. So now we can go back to our work energy equation. The elastic potential energy in the spring is this formula here. So that's kind of nice, pretty simple. All right. So again, we're free to set the baseline wherever we start for potential energy equal to 0 at any convenient spring extension. So wherever we want to start is where we can start. An obvious choice is to set 0 at the spring's equilibrium point. So we can make that x equals 0. We can make that where our potential is 0. So if we do that, then we have this. U sub s equals 1/2 kx squared. So assuming U sub s equals 0, when the end of the spring is at x equals 0. So if we look over here at the little example, we have an Achilles tendon situation. So we're looking at a human foot. On each stride, the tendon stretches, storing energy. So as you walk, the calf muscle is connected to the Achilles tendon. And as you walk, it gets stretched, so it acts like a spring. And then as you continue your stride, it relaxes, and then it stretches and it relaxes. So it's acting like the string is being stretched and compressed and so on. So when you run, your feet repeatedly stop and start. When your foot strikes the ground, it comes to rest, losing kinetic energy. It says about 35% of this decrease in kinetic energy is stored as elastic potential energy in the stretchable Achilles tendon of the lower leg. On each plant of the foot, the tendon is stretched, storing some energy. The tendon springs back as you push off the ground again, helping to propel you forward and returning the stored elastic potential energy back to kinetic energy, recovering this energy that would otherwise be lost and thus increasing your efficiency. So the human body has these potential and kinetic energies going on within it all the time. So anyway, I don't remember now if I talked about this right here. So U sub S depends on the square of the displacement X. U sub S is the same, whether the spring is stretched or compressed. So we're operating as a square situation. Okay. The energy stored in a stretched tendon. So back to the Achilles. The Achilles stretches when you run, and so this stores some energy because it's stretched. Energy that is returned when you push off the ground with your foot. So this figure here shows smooth data for restoring force versus extension for the Achilles tendon. It would never look like this if you actually collected data. It would be very choppy, but this is smooth. So this is attached muscle in a female subject. When she runs, at one point in her stride, the stretch reaches a maximum of 0.5 centimeters. So the question is, what energy is stored for this stretch? So in the figure, we have the extension along the x-axis and the restoring force along the y-axis. So we have the equation for what energy is stored. So that means we need to use U sub S, the energy that's stored in the stretch for the spring that we're considering this is, equals 1/2 kx squared. So this is the formula that we're going to be using. Now, we already know that they told us the delta x maximum here was 0.50. So we're going to write that down. Delta x is 0.50 centimeters. And we'll convert that to meters here in a little bit. Actually, I can just do that now. So 0.50 centimeters would be how many meters?
0.0050.
Yeah, we got to move the decimal 2 spots. 0.005 meters. Okay. And then, so that's our delta x in meters. So we already know the x. We need to figure out the k. How are we going to do that?
We could use the graph.
Yes, we're going to use the graph. How?
So when her maximum force is at what was it, 0.5? So she would.
What is the K? Do you remember?
A constant.
It is a constant. It is easily calculated using this graph. Do you know what it is? It's the rise over run. It's the slope. Yeah.
That's what I was trying to say. I just couldn't say it.
So all we have to do to calculate the K is calculate the slope, which means we just need 2 easy points.
100 over points.
I would go even further than that just to increase our accuracy. Make our dots as far apart as possible. So we have an easy point right there. And
0, 0.
0, 0. As far apart as possible. Okay. So now K equals
slope. So y.
y2 minus y1 over x2 minus x1.
So 400.
400 newtons.
0.0024 meters.
So that's y2 minus y1. Y1 is 0 newtons.
Yeah.
Divide by x2, which is
0.0024.
You're converting that to meters?
Yeah.
Okay. 0.0024 meters
Minus 0.
-0 meters. Good. I just wanted to get that completely on there. So now we can do this calculation. The minus zeros are irrelevant for this calculation. So we have 400 divided by 0.0024. What do we get?
I'm gonna say there's 4 zeros in this.
No.
16. Wait. 166,666.
I think your decimal is a little
Yeah.
off.
There's no
One-
way that's huge.
16666.
What do you get?
166667.
Yeah, 16,666.
Oh,
0.6 repeating, right?
Yeah.
Yeah.
Now the units will be newtons per meter. Okay, so we have our K. So we can go ahead and do our formula here. We have U sub S equals 1/2 times the K, which was it's 1.67 times 10 to the 1, 2, 3, 4. I'm not going to mess with that. Never mind. Get rid of that. 1.6666. I have it all. 0.6 repeating. Just use your calculator's answer though. Newtons per meter, and then times the 0.005 meters, but don't forget that it's squared. What do we got?
2.083 repeating.
2.083 repeating. What are the units on this one?
Joules.
Joules, and then significant figures here. Now that we're at the end, finally, we do significant figures.
2.1?
Looks like probably 2.1 joules.
It's more reasonable.
All right, so energy stored in the Achilles tendon, 2.1 joules. A lot? A little? Don't know?
Not enough.
Well, compared to the going up the flight of stairs.
Go ahead, running up the Empire State Building, not nearly as much, right?
Mhm.
But we're talking about a slight stretch in the Achilles tendon in the human body
Probably.
as we're running. We're getting 2.1 joules every single step.
Not
So
enough.
could it be more?
Yeah.
Maybe, but 2.1 every single time.
That's my bio.
All right, so when a spring is stretched by 5 centimeters, its elastic potential energy is 1 joule. What will its elastic potential energy be if it is compressed by 10 centimeters?
Probably gonna cut this bit out.
C.
D.
Why D?
X is squared.
X is squared, true. What does that do?
Yeah.
2 squared is 4.
2 squared, where's a 2?
It's exponential.
It's not exponential.
It's not. It's linear. So it's C then.
No, I didn't say that. Exponential means that the exponent has the variable, but it doesn't. So it's not exponential.
So, well, you're squaring it. So
Okay, I'm squaring what?
the thing that we're stretching it. The meters. Distance.
5 got squared, right?
Yeah.
So 5 squared is
25.
okay. Then 10 would be squared also, right?
And the difference between that is 4.
The factor.
Yeah, the factor is 4. Is that the same for everything?
I don't know what you mean. But the
So-
factor here is 4. So the answer
So
is B.
if 3 squared is 9,